Dear students, my name is Dr. Amir Fawaz Zahoor, and in this video we will talk about 1,2 difunctionalized compounds. For this we can consider a few examples. For example, this diketone, this is 1, this is 2, and it can also be called alpha diketone, or we can consider this carbon 1, carbon 2, alpha hydroxy acid, alpha hydroxy carboxylic acid. We can also consider two amino alcohol. This is 1, 2, 2 amino alcohol. Or for example, we can consider beta hydroxy sulfide. So these are few examples which have 1-2 relationship between two functional groups, and if we take the example of this molecule, we disconnect it from here, and as a result of this disconnection we would get this acyl group with positive charge and the second acyl group with negative charge as synthone. Now we can see the natural polarity of carbonyl group is positive charge, and these are generally accepted synthones, whereas in this case we have negative charge, so it means here we have the problem of ompolum. And we have already discussed about ompolum in our previous lecture when we studied 1,4 difunctionalized molecules. So here we have ompolum, and if we disconnect from here, for example, and as a result of disconnection we get this synthone. This is acceptor synthone, and we know that for this we have reagent, this ketone, so reagent for this is available. And on the other hand, we have carboxylic acid with negative charge on carbonyl group, like this one with negative charge. So here also we can see carbonyl carbon is getting negative charge in synthone or negative polarity, so this is again ompolum. And here we can disconnect from here, and we can see we have RNH negative as a result of disconnection as donor synthone, and we get positive here. And when we get positive here, it means the positive in principle comes here, the carbon which has an electronegative atom or group gets positive, and then here should be negative, but here we have positive. It means we see again ompolum here, reversal of polarity. Similarly, the case is same here. When we disconnect from here, we get, as a result of disconnection, RS negative, and again positive here. This case is same, and again ompolum is observed. So again ompolum is observed here. So these are the examples of 1,2 difunctionalized compounds where we have the problem of ompolum. Now we have some special reagents for the synthesis of all these molecules, and we will discuss them one by one. So first reagent which we will discuss is 1,3-dithiene, and its structure is this one. And because two sulfurs are at 1,3 relative position, so this is called 1,3-dithiene. It can be 1,2-dithiene, the isomeric form, or 1,4-dithiene. And this is analogous to the oxane derivative, dioxane, 1,2-dioxane, here we have 1,3-dioxane, then 1,4-dioxane. And I hope you are well familiar with 1,4-dioxane because it has been used, or it is used in organic reactions as a solvent. So, but our concern is about 1,3-dithiene. So I just remove the others. And why we are concerned with this? Because this carbon has hydrogens, and due to the larger size of sulfur, it has polarization effect, and as a result the hydrogens which are present here are acidic, and they have pK value 31. So if we use a stronger base, for example N-butyl lithium, we can abstract the proton from here, and as a result of abstraction of proton, this anion is formed, and this anion can be used as nucleophile. So now we discuss how it works. A dithiene is basically a cyclic thioketal or acetal. For example, if we have this aldehyde, we react it with 1,3-propane dithiol. Generally 1,3-propane dithiol is used in the presence of acidic conditions, or we can take a Lewis acid, for example BF3-diethyl etherate. It exists as a complex, and it results in 6-membered 2-sulfur containing heterocycle called 1,3-dithiene. Now we have this hydrogen available which can be abstracted by N-butyl lithium, and for example we use N-butyl lithium here. It is abstracted, and as a result we get this anion, and during this the butyl group, which has negative charge, abstracts this proton, and N-butane is eliminated. Now because there is no electrophilic center which can be attacked by N-butyl group, therefore we have no problem in choosing N-butyl lithium as a base, because in our previous lecture we discussed that N-butyl lithium can result in nucleophilic additions, for example, or substitution reactions, and therefore we have to be careful while choosing N-butyl lithium as base. So N-butyl group takes this proton and converts into N-butane, and this lithium surrounds this negative charge, and this reagent is also known as Corey-Seebach reagent. And this is nucleophilic in nature because it's anion, and we can react it with, for example, aldehyde, and it would attack here, and this bond will break. And in the first step we add aldehyde, in the second step we add acidic water. Generally, we have discussed earlier as well that when we start a reaction with a base, the reaction is generally quenched with acidic water. So we will get this, and in the last step we can remove or deprotect this. We can deprotect this using hydrolysis with HgCl2, or we can use acidic water as well, as some books report this, the use of this as well. So we get this molecule. Now if we look closely, for example, if this molecule is our target molecule, alpha hydroxyketone, if this is our target molecule and we disconnect this from here, then as a result of disconnection we get acyl group with negative and this group, this synthone, with positive. And this is a standard synthone, and we know that already. We have studied the reactions of this synthone a number of times, therefore this can be used as synthone. Whereas here we have the problem of umpolum, and with this reaction we have seen that if we use this reagent, it can serve as acyl anion equivalent for this reaction. So when we have the target molecules like this, we can choose these 1,3-dithiones as a reagent, as acyl anion equivalents, to prepare these molecules. So 1,3-dithiones are synthetically very important molecules. They can be used in a number of transformations, and we can see few examples. First, I write here the acyl anion, and its equivalent is dithione, 1,3-dithione, and it has a lot of applications. It is also known as Corey-Seebach reagent, we have just discussed, and we see different conversions which can be carried out using dithiones. Using 1,3-dithiones, we can convert formaldehyde involving protection deprotection methodology, because we have to convert this first into dithione and then we have to hydrolyze back after the desired reaction into aldehyde, or we can convert this into ketones. These can be symmetrical or non-symmetrical. And how we will carry out this? We take this formaldehyde, we treat it with 1,3-propane dithiol in the presence of acid, and we convert this into dithione, and we can use N-butyl lithium to abstract this proton to form Corey-Seebach reagent, and this would be allowed to react with any alkyl halide. It would attack here, and halogen or halide will be eliminated via in general SN2 reaction via nucleophilic substitution reaction. And we will get this. And after hydrolysis using HeCl2, we will get the aldehyde. So this one. And if we treat it again with N-butyl lithium, again we will have Corey-Seebach reagent, and this can be reacted with similar alkyl group Rx or a different alkyl group R1X, and as a result of this we will get this or this one. If we hydrolyze this, we will get symmetrical ketone Cl2 water, and if we hydrolyze this using the same conditions, we will get non-symmetric ketones. So using this sequence of organic reactions, protection and deprotection methodology, we can get aldehyde or symmetrical and non-symmetrical ketones. And then we see further next possible conversion. Second is conversion of aldehyde into alpha hydroxy ketone. This we have studied. And then third one is conversion of this aldehyde into alpha diketone. Now how this would work? We will take the aldehyde and again we will convert into the corresponding dithiene, this one, and then with N-butyl lithium we will get the Corey-Seebach reagent, and it will be treated with nitrile, and we know that nitriles are electrophilic in nature. This would attack here and we will get negative charge here on the nitrogen. Lithium will surround it and we will get this. Now upon hydrolysis we will get this one. This would be hydrolyzed to corresponding keto group, and then hydrolysis with HeCl2 water, we will get alpha diketone. Here we will use heat, and if we can use acidic water, we can directly convert this molecule into this one. So this is how we can prepare alpha diketones. Now we see next conversion. 1,3-dithiones can also be used for the preparation of beta hydroxycarbonyls. Beta hydroxyketone, and how would this work? We can use Corey-Seebach reagent, as we have prepared a number of times, so now we can use directly negative, lithium positive, and we will allow it to react with epoxides, and it will attack here, and after the reaction is quenched we will get this molecule, which can be hydrolyzed again using AgCl2 water, to get beta hydroxyketone. So using epoxide and Corey-Seebach reagent we can prepare beta hydroxyketone. So this conversion can also be carried out using this methodology and using 1,3-dithiones. If we use aldehydes and again we use Corey-Seebach reagent, we can prepare alpha keto carboxylic acids or their esters. For example, this Corey-Seebach reagent can be reacted with carbon dioxide, and we will get this one. If we treat it with H plus or H3O plus, we will get the corresponding alpha hydroxy carboxylic acid, this one. Or if we treat it with any alkyl halide, we will get the ester here, like this, and then if we hydrolyze this, we can convert this into corresponding ester. So these are few of the important synthetic transformations which 1,3-dithiones can be used to carry out. So I hope this is clear to you. Now we see the application of 1,3-dithione towards the synthesis of bark beetle pheromone. And this has been done using this aldehyde and using 1,3-propane dithiol under acidic conditions. It was converted into corresponding dithione, and then with N-butyl lithium this reagent was formed, which was then reacted with this special alkyl halide, and after nucleophilic substitution reaction, this was formed, which was further hydrolyzed using mercury chloride and water to get this one. This was then further reduced with sodium borohydride and this is the bark beetle pheromone. So this is the synthetic application of 1,3-dithiene towards the synthesis of bark beetle pheromone. Now we see the next reagent. So next case is the use of cyanide ion as equivalent of carboxylic acid anion, and we know that if we have this type of synthone, we do not have a reagent for this type of synthone. So therefore we can use cyanide ion as equivalent to this synthone, and we can use this synthone or reagent for the preparation of compounds like this. And the synthetic procedure involves the reaction of corresponding aldehyde or ketone. It can be reacted with HCN, and as a result of the nucleophilic addition we would get this molecule, and this can further be hydrolyzed using H plus H2 into corresponding alpha hydroxy carboxylic acid, or we can hydrolyze in the presence of acid and alcohol, for example ethanol. We can get corresponding ester derivative. So if we have molecules like this, or this alpha hydroxy acid, carboxylic acid, we can use cyanide ion as equivalent to this type of synthone. Now we see next reagent. Next reagent is epoxides for the synthesis of 1,2-difunctionalized molecules. For example, we have this epoxide, and epoxide is synthetic equivalent to this synthone, and we know that here in general negative should have been here, but we have positive here. It means it is the case of Polung, as we have discussed earlier. So we can use epoxide as an equivalent for this type of synthone, and if it can be reacted with different nucleophiles such as amine, the amine would attack here, and after ring opening reaction we will get beta amino alcohol or 2-amino alcohol. So this is one type of molecule of 1,2-difunctionalized molecule which can be prepared using the reaction of amine with epoxide. We can also use thioalcohols, and they would also attack in the same manner or react in the same manner. In general, the ring opening reaction occurs by the attack of nucleophile at less hindered carbon, and as a result of the reaction we get beta hydroxysulfides. So if you call it 1, this would be 2, so 1,2-difunctionalized molecule. And if we use alcohols for ring opening reaction, same would happen. This would take place in the presence of a base, because in general the alcohols are not good nucleophiles for SN2 type reactions, and they have to be converted into corresponding anions, and therefore a base would be required for this reaction. And as a result of the reaction, we will get these compounds. So in this lecture we have discussed 1,2-difunctionalized compounds, and we discussed the examples of 1,3-dithiones, use of cyanide, as well as the ring-on-ring reaction of epoxides for the synthesis of 1,2-difunctionalized molecules. I hope this is all clear to you. If you have any question or query, please leave them in comment box. Thanks.